Imagine two tiny charged particles suspended in an absolute vacuum. There are no strings attached to them, no physical tethers. Yet, as they drift through the void, they suddenly accelerate toward one another. One object clearly alters the trajectory of the other across empty space. They never make physical contact, but they communicate their presence instantly. Depending on the specific properties of these particles, they will either snap violently together or forcefully shove each other away. Understanding exactly how this invisible push and pull transmits across a vacuum is the starting point for a concept known as Coulomb's law. This interaction is not random. It is governed by precise, predictable mechanics that dictate the behavior of physical matter everywhere. Electric charge comes in exactly two varieties: positive and negative. The rule of electrostatics is simple. Opposite charges, one positive, one negative, attract and pull inward. Identical charges repel and push outward. But the strength of this interaction fluctuates. Sometimes the push is weak, and sometimes incredibly violent. If the strength of the interaction changes, there must be exact mathematical inputs determining how hard those particles push or pull at any given moment. To figure out what controls this force, we have to isolate the variables. First, we lock the distance between two objects completely in place. Then, we pump more internal charge into them. As the total amount of charge on either particle increases, the force vector lengthens. The physical force scales up in direct proportion to the amount of charge. Now we run the second test. We freeze the charge magnitude so it stays exactly the same, but we pull the particles further apart in physical space. The force immediately drops off. But if you measure this drop carefully, you notice the decay isn't a simple straight line. Charge acts as the fuel, strengthening the interaction, while spatial distance acts as a severe, nonlinear dampener. Uncovering the exact math behind this required a highly sensitive physical experiment. In the late 1700s, French physicist Charles-Augustin de Coulomb set out to measure this invisible interaction. He used an apparatus known as a torsion balance. By bringing a charged sphere near another suspended inside a glass chamber, the invisible repulsion caused a thin wire to twist. He could then measure the exact angle of that twist to calculate the physical force. The measurements pulled from that twisting wire confirmed our earlier thought experiment. The force tracked perfectly with the amount of charge and dropped as the spheres moved apart. He formalized this into the equation we use today. The total electric force, F, is equal to the product of both charges, labeled Q1 and Q2, divided by the square of the distance between them, represented by r squared. The equation directly translates the mechanics of empty space into a predictable, usable law. The denominator is where the most aggressive math happens, the distance squared. Take a look at this graph plotting the force against the distance. Because of that square, if you double the distance between two charges, the force drops to exactly 1/4 of its original strength. Triple the distance, and you have just 1/9 of the force. Because the force dies out so incredibly fast over space, the immense electrical forces locked inside every atom cancel out at a distance. That steep mathematical drop-off is the exact reason everyday objects don't violently push or pull on each other. Up close, at the atomic level, Coulomb's law dictates reality. It's the calculation keeping negatively charged electrons bound to positive atomic nuclei. Scale those millions of tiny interactions up, and you get everyday phenomena, like the static cling that sticks a balloon to a wall. Even massive events, like a lightning bolt ripping through the atmosphere, are simply point charges reacting to one another on an unimaginably large scale. Every electrical interaction starts with two charges and the space between them. To understand electric fields, electric potential energy, or the circuits powering modern life, you have to start with the mechanics of Coulomb's law.